The subject of this program is the replacement of a lifted or missing supported through-hole land with no inner layer connections. A supported through-hole is one in which the hole is plated or coated with a metal lining around the inside of the drilled hole wall or barrel. Supported through-hole lands sit at the top or the bottom of these metal-plated holes. The plating extends through the hole to the lands at the top and bottom, forming one continuous metal mass. The lands and the plating are connected in two ways. The first way the lands and the plating are connected is mechanically. This means that there is a physical connection between the lands and the plating. The physical bond is strong enough to withstand the normal wear and tear of electronic products. The second way they are connected is electrically. The lands and plating are parts of the same circuit. Any time a land is torn away from the plating, the mechanical and electrical connections between the land and the plating is damaged and should be restored. The method for restoring these connections is to replace the old plating with a device called an eyelet. If you can see that the plating at the top, bottom, or inside the hole is cracked or chipped, the original plating should be removed and a replacement eyelet inserted. One exception to this rule is when a corner of a land is lifted and the plating inside the hole is undamaged. Assuming that the land can be reused, the lifted portion can be rebonded to the board surface using the dry film rebonding technique we learned earlier in this repair series. The eyelet insertion procedure can be used on single-sided, double-sided, and multi-layer boards. However, unless you have special training, you should not use the eyelet insertion procedure on certain types of plated through-holes. As you know, multi-layer boards have two types of plated through-holes, those with internal electrical connections and those with external electrical connections, or surface conductors only. An inner layer connection is one where the connection to the plated through-hole is made inside or below the surface of the board. Eyelet insertion on a plated through-hole with internal electrical connections is a complex procedure and is not described in this tape. We will only cover the eyelet insertion procedure for plated through-holes with external surface conductors. Let's begin the repair process with an analysis of the damage. When analyzing plated through-hole damage on multi-layer boards, first check for inner layer electrical connections. The most reliable method for discovering if there is an inner layer connection is to review the engineering schematics, sometimes called the artwork, for that particular multi-layer board. Next, look for board damage and repair it if necessary. If the land is partially lifted, check to see if the plating around the inside of the land is cracked, chipped, or separated from the land. If the plating has been damaged, proceed with an eyelet replacement. Now let's begin the actual repair work. We'll start by cleaning the repair area. Then remove any contamination or solder masking if necessary, and clean the area once again. Next, we'll select a replacement eyelet. Most eyelets come from the manufacturer with a flattened surface on one end called a flange. We will call this prefabricated flange the factory flange. A technician makes the second non-factory flange by flaring and flattening the material that sticks through the other side of the hole after the eyelet has been inserted. The selection of the replacement eyelet requires some simple math. To do the math, you have to make several measurements. We'll explain what these measurements are right now. All measurements can be made in the metric system of measure, centimeters, millimeters, etc., or in the English system of measure, inches, feet, etc. For the purpose of this program, we will use the English system. The first measurement that must be made is the overall thickness of the board. Board thickness is measured in thousandths of an inch, or mils. If a board is measured at 62 thousandths of an inch thick, you may hear the term, the board is 62 mils thick. Next, we'll look at the inside diameter, or ID, of the replacement eyelet. The eyelet diameter should always be between 3 thousandths and 20 thousandths of an inch greater than the diameter of the component lead that will go through the eyelet. In other words, the inside diameter of the eyelet must be bigger than the component lead, but not too much bigger. Another critical measure is the length under the flange, also called the luff. This is the total length of the eyelet minus the thickness of the factory flange. This length should be between 25 and 35 thousandths longer than the thickness of the board. The protruding portion will be flattened or swaged to form the flange on that side of the board. In other words, the inserted eyelet needs to stick out of the board enough to create a flange. FD is flange diameter, or the width of the factory flange. The eyelet's factory flange diameter should be slightly smaller than the land it sits on to provide for an acceptable solder fillet. Acceptable solder fillets are described in IPC's publication A610, Acceptability of Electronic Assemblies. This specific information can be found in the section on soldering. The next measurement is called the outside diameter of the eyelet, or OD. The hole that the eyelet goes into can be between 1 and 5 thousandths larger than the eyelet's outside diameter. The hole should be big enough to allow the eyelet to be inserted without force, but small enough so that the eyelet fits snugly. Not too tight, not too loose. Let's review an example to show how a typical eyelet is selected. The first step is to measure the thickness of the board using a dial caliper or a micrometer. Place the board between the jaws of the caliper or the measuring faces of the micrometer and move the ends together until they lightly touch either side of the board. Then check the reading. For the sake of our example, let's say that we have measured a board and it's 62 thousandths or 62 mils thick. Now let's find the flange diameter measurement. To get this measurement, locate one of the other undamaged holes that the through-hole component used. This is sometimes called a sister or companion hole. We'll measure the diameter of the land above the companion hole. The preferred diameter of the factory flange on your replacement eyelet should be slightly smaller than the companion hole's land. It can't be any smaller than the hole in the board or the eyelet would fall out. It also can't be so large that it interferes with the minimum spacing requirements of nearby circuitry. For our example, the companion hole's land measured 95 thousandths in diameter. Now we need to find the inside diameter of the replacement eyelet. As mentioned earlier, a correct amount of space between the component lead and the eyelet wall is within the range of 3 to 20 thousandths. The eyelet ID has to be large enough to leave space between the component lead and the inside wall of the eyelet. This space will allow solder to wick up through the eyelet all the way to the top of the hole. However, if the space between the side of the lead and the inside wall of the eyelet is excessive, the molten solder won't stay up in the barrel. It may just flow back down, or cause pits, voids, or insufficient solder coverage. A typical method for a technician to measure the ID of an eyelet is to use a set of pin gauges to measure the inside diameter of a companion hole's barrel. We know that the inside diameter of our eyelet must be very close to or the same size as the inside diameter of the companion hole. Remember that the leads of the replacement component that will go in both holes are the same size. So, for the sake of our example, let's say that the ID of the companion hole is 40 thousandths. The next measurement we need to find is the OD, or outside diameter of the eyelet. To find this measurement, you must know the diameter of the hole that the replacement eyelet will fit into. The diameter of the hole will be the same size as the diameter of the drill bit or the ball mill you use to remount the hole. Remember that in order for the component lead to fit into the repaired hole, we must grind all of the damaged plating out of the hole. So we'll select a ball mill or drill bit that is slightly larger than the measurement of the companion hole's diameter. This slightly oversized mill or drill bit will grind out any remaining debris in the damaged hole. However, the bit or mill should not be so large that it digs into the board's material behind the plating. The diameter size of a bit is stamped on the shank or the part that is inserted into the chuck of the drill motor, or on the drill bit holder. It's always a good idea to double check the diameter of the bit or mill with your caliper. Ball mills come in sizes from number 1 to number 8. Each number corresponds to a diameter size. For instance, a number 1 ball mill is 31 thousandths in diameter. A number 5 is 63 thousandths. The outside diameter of the replacement eyelet must be 1 to 5 thousandths smaller than the reamed out hole. This will allow the eyelet to be inserted without force but not rattle around inside the hole. For this example, let's say that we'll use a number 5 ball mill. A number 5 ball mill is 63 thousandths in diameter. To find this outside diameter of the eyelet range, we'll take .063 and subtract .001 and get 62 thousandths. Then take .063 and subtract .005 and get 58 thousandths. The range for the outside diameter of the replacement eyelet is between 62 and 58 thousandths of an inch. Let's continue with our example for selecting a replacement eyelet. The next measurement to make is the length under the flange, or luff. The luff needs to be 25 to 35 thousandths greater than the thickness of the board. This will give us enough extra material to make a proper second flange. Remember that the board thickness was 62 mils, or 62 thousandths. To find the luff, first add .062 to .025 to get 87 thousandths. Then add .062 to .035 to get 97 thousandths.